Hello, statistics students. There were some questions on type 1 and type 2 errors, so I'm going to go over those again. This comes from doing hypothesis testing. So let me just give a quick example. Like, we believe, there's this new IQ test out there, and we think it's giving people higher scores than they usually would. IQ scores are standardized, kind of adjusted so that the mean is always at 100, so we can compare it with other IQ scores. So we set up a hypothesis test with the null being that the mean equals 100, and the alternative hypothesis is that the mean is greater than 100. And for those of you who are wondering about parameters in statistics, we write a null and alternative hypothesis with the parameters. We say the population mean should be 100, and the population is, we're going to test and see if it's greater than. This will be a right-tailed test, by the way. It's pointing to the right. We do statistics to test. So we take a sample, we score a whole bunch of people, and we get a sample statistic. You notice this is a different symbol right here, X bar, and it equals 110. Okay, so the hypothesis test is set up with the parameters. The testing is done with a sample statistic. I'm not going to go into p-value calculations very much. I just want to talk about the errors. So we test and see how likely it is to get our result. Let me go back to that. We assume that the null hypothesis is true. We test. How likely is it to get our result, or more extreme, given we think this is true? That's our p-value. So we find our p-value, how likely it is, and we either reject the null hypothesis or we fail to reject the null hypothesis. Those are the two choices we make. It's when we do this that we come up with possible errors. Now, if we reject the null hypothesis and the null hypothesis wasn't true, yay, that's good. If we fail to reject the null hypothesis and the null hypothesis is true, then that's good as well. No errors there. Now, a type 1 error comes from doing this first step, reject the null hypothesis, but it was really true. So in terms of the IQ test, you reject the null hypothesis that the mean really was 100 because your result was 110. However, there were some possible errors in there. Maybe you didn't randomly select people, or maybe you managed to select some people who are just scoring high for some reason. They're just all smart. It could happen. So the question is, how often do you want to reject the null hypothesis and be wrong? How often do you want to commit a type 1 error? Well, if you never reject the null hypothesis, so you're never wrong, why'd you do the test in the first place? If you always reject the null hypothesis so that you're close to 100% wrong, again, why did you do the test in the first place? Well, we do some rejection, but we try to minimize this type 1 error. We make it kind of small. We set a low cutoff, and down here, somewhere between 0 and our cutoff, is what we call a rejection region. We will reject the null hypothesis if our p-value is down in this rejection region. Now, by tradition, I guess, we're willing to accept a 5% cutoff. We'll be wrong about 5% of the time, but 95% of the time, if I was right 95% of the time and I was on the stock market, hey, I'd be a billionaire. Okay? I can handle being wrong about 5% of the time. So, you set up your alpha. You find your p-value, and then you see whether it's in your rejection region or not. Remember, your p-value is the probability of getting your results, or more extreme, if your null hypothesis is true. We call it a p-value because it's short for probability. Don't know why we couldn't call it the probability, but that's just what we do. So let's say we get a p-value that's less than alpha. Then it's in the rejection region, and we reject the null hypothesis. So a p-value of 0.03 would be between 0 and 0.05, so I would reject the null hypothesis. If my p-value was bigger than alpha, I would fail to reject the null hypothesis. So let's say I had a p-value of 11% or 0.11. Sorry about that. Then I'd be wrong about 11% of the time. I don't like that. I will fail to reject the null hypothesis. In this case, right here is where I fail to reject the null hypothesis. It's outside of my rejection region. So, a type 1 error is definitely controlled by your alpha. You set up where you want to reject the null hypothesis. Okay, so that's a type 1 error. Obviously, the type 2 error is going to be where you select the second option. You fail to reject the null hypothesis, but it really wasn't true. This one is harder to control for. If I was going back to the IQ test, I failed to reject the null hypothesis because 110 is really close to 100. Maybe my sample wasn't big enough. Maybe my test was administered correctly. Maybe my cutoff point was too low. And let me show you this. A type 2 error is harder to control for, and we usually just have to get a large sample and a really good way of measuring. And just like a type 1 error is controlled with alpha, well, a type 2 error is called beta. And beta happens if your sample wasn't large enough, your data has too much variation, your alpha is too small, or your test just wasn't good enough. So if you have a really small sample, it can be really hard to see any difference and say, oh yes, I should reject the null hypothesis. You just say, my data is inconclusive, so I will fail to reject the null hypothesis. Well, if you get a lot more sample, you can see a difference, and that can help you reject a null hypothesis if there really is a difference. Sometimes the data really kind of likes to get close to each other. Well, that's where your large sample comes in. So, sometimes your alpha is just too small. If you've got a rejection region that's only, say, 1%, well, you'll only commit a type 1 error 1% of the time, but your type 2 error will happen a lot more often. If you can just raise your alpha to, say, 5% or even 10%, you might be less likely to commit a type 2 error where you don't, remember, a type 2 error is where you reject, or fail to reject, sorry. You fail to reject the null hypothesis, but you really should have. A lot of times when people do studies on other people, they'll say, this is significant at the 10% level. This is significant at the 5% level. This is significant at the 1% level. They adjust their alpha so that they can, be less likely to commit a type 2 error. What if your test isn't good enough to actually detect whether or not the null hypothesis is true? You can spend more money and build a better test, but you've got to weigh it. Is it worth the money or not? Worth money and time. Statistics tests do take money and time. Okay, so a type 1 error comes when you say reject the null hypothesis, but you're wrong. A type 2 error comes when you say fail to reject the null hypothesis, but you're wrong. So you notice we've got more words here. So first, second. Type 1 error is easy to control. Type 2 error is a lot harder and it can take money. So I hope this summary or this PowerPoint helps you guys.